African Astronomical Observatory in Cape Town. I got to build some cool like vacuum table things for them there. My research currently is more sciencey than it is engineering. I'm looking at like charge exchange between materials. Thankfully, that's not what this presentation is about. In this presentation, I'm going to be talking about asteroids and near-Earth objects. So let me start off by saying, what is a near-Earth object? Those are asteroids and comets whose orbits are close to Earth's, or they come close to Earth. So fun fact that I learned last night, Halley's Comet is a near-Earth object because of how close it passes to Earth. And so the picture with all of the orbits that you can see is there are different types of orbits that an asteroid can be in, and then it is designated as a near-Earth asteroid. So these asteroids are different from the main belt asteroids that are in the asteroid belt. And so we use different classifications to talk about these asteroids. They're classified according to what type of orbit they have, what they're made of, their composition, and also can they be a potential hazard to Earth. So the asteroid picture that you see on the screen is a picture of the asteroid visited by the OSIRIS-REx mission. And that asteroid has like a 0.001% chance of impacting the Earth. For example, I think that's the numbers around about there. And so that's why we visited, because we were like, oh, what is it made of? What is it doing? Why is it there? It's important to us. So some of the motivations for exploring these near-Earth asteroids and these objects are mainly science purposes, and also to look at planetary defense. So what happens if they are on a collision course with Earth? So I've said the words planetary defense a lot. Planetary defense is mainly when we're talking about defending the Earth against asteroids and comet impacts. So it's not when you're thinking about like a satellite falling or a rocket that nobody takes care of and then it accidentally falls into an ocean. So this is only for asteroid and comet impacts. And so there are two ways in which you can kind of like defend the Earth against these possible impacts. Is you can either disrupt the asteroid and break it into so many pieces that it's not going to impact the Earth anymore, or you deflect it so that it's on a different path. And the aim in doing this is you want to have the least amount of negative effects to the environment, and also you want to be sure that in the future it won't go back on a collision course with Earth. So the first actually planetary defense mission, was the DART mission. And so in this mission, they sent a spacecraft to the Didymos, so Dimorphos and Didymos, sorry, that picture is a little old. So they sent a spacecraft to the binary system with Didymos and Dimorphos. And so Dimorphos is the smaller one that the spacecraft impacted. And then they kind of looked at what happens when you impact an asteroid, what happens to it, and what is going to happen to its orbit and to its properties, and kind of like how the impact works. So this binary system had no chance of ever impacting the Earth. It was just an exercise to give us more information on like how deflection missions work. So this is just a cute little patch that we designed for the mission I'm going to be talking about right now. As John mentioned, we presented this work at the Planetary Defense Conference. And this conference happens, I think it's every 2 years, I think, I could be wrong. And so whenever they have this conference, they have a planetary defense exercise that they do. And so before the conference, they release some information on the asteroid or the object that's going to impact the Earth. And it has different parameters, such as like different orbits and weights, materials that it's made up of. And so during the conference, part of the conference is going through this exercise of designing a mission to mitigate this like potential hazardous threat. And so for our project, what we did is we took the preliminary information given by the conference, and we designed a mission start to finish, spacecraft design, all of those types of things to think about. If this asteroid was coming to the Earth, how would we mitigate it? So the asteroid parameters that were given, so it had a fairly large range in diameter and mass. These were 10th and 90th percentile mass numbers. And so the orbit of the asteroid is out of phase with Earth, and it makes no close approaches until Earth impact. And so that's very important because there isn't a way for us to study the asteroid in more detail until it actually impacts the Earth. And that fact critically influenced our design. So here we can see just a description of the orbit. So the picture on the left is just a top-down view of Earth's orbit, and then the 2023 PDC, that's the asteroid orbit. And then on the right, you can see like a 3D version of that, of the same orbits. And what we can see is that the asteroid orbit is very inclined, which is a problem when you're trying to get there and you only have a specific number of mass and you have a big velocity change that you need to get there. So it's very inclined, and then we can also see that impact point is where the asteroid and the Earth orbits cross at those two nodes. So here is a total mission timeline to kind of just think about while I'm talking. So the asteroid this is a hypothetical asteroid. It would be discovered in 2023, which is where we are now. And then it would impact the Earth in 2036, which is 13 years from now. And so our THEO and MUFN missions, we designed them so that they launch and reach the asteroids at specific points. THEO is a rendezvous mission that gives us data about the asteroid, and then MUFN is our mitigation mission. All right, so moving on to our exploration orbiter, our rendezvous mission. So this spacecraft was designed so that it would rendezvous with the asteroid. And what that means is that it would reach the asteroid and then move into an orbit around the asteroid so that it could take some pictures there and get some data about how big is the asteroid, what is it made out of, what is the topography of the asteroid, and that information is crucial to know when designing a mitigation mission. The THEO would also have a 12-year final lifetime so that it can stay and observe the mitigation mission. And it has a very short 2-year development time. That's not very common. And we chose this because we had a very short timeline in which to actually mitigate this asteroid. And so because of this 2-year development timeline in the design specifications of THEO, we focused on using commercial off-the-shelf components that have already been designed and that we can just go buy and put on a spacecraft and send it into space. So the trajectory design of THEO, the figure here, it's called a pork chop plot. And so this figure shows you your maximum mass delivered to the asteroid, depending on when you choose to depart and arrive at the asteroid. So we used charts like these to pick out when would be the best time to launch, and then also figure out how much mass we have to work with at the start of our mission, because knowing how heavy your spacecraft can be is very important. So from this pork chop plot, we have 2 launch periods. So this is our main launch period. it is a launch window of 21 consecutive days. So NASA requires a launch period to be, I think, 21 consecutive days. And what that means is we can launch on any one of these days and with our spacecraft, and we would successfully arrive at the asteroid and be able to complete our mission. So the figure in the bottom that you can see is kind of like what our orbit would look like. So our launch vehicle that we chose, which is a Falcon 9 expendable or a Falcon Heavy, it's somewhere in the slides. So our launch vehicle would put us into the orbit of the asteroid. And so what that means, it's very good for us, is the launch vehicle takes care of our inclination change. So that means that our delta V, or the change in velocity that we need to rendezvous with the asteroid, is very small. It's about 2.6 kilometers per second. In the grand scheme of things, it's very small, although that's for this specific mission, although it's still quite a large number when you compare it to other missions. So we have a second launch period that looks pretty much the same. It's just a bit of a later date. And so here we can see that regardless of which day we launch, our arrival is on the 26th of May, 2026, and we just have different delta Vs. And so the launch C3 is an indication of how much energy the rocket needs to expend to put you into your orbit. So what we can see here is when we need less delta V, the rocket needs to use more energy to put us into our orbit, and vice versa. So once we get to the asteroid, we have a few different arrival maneuvers that we're doing. So we have a survey orbit, a high altitude, low altitude mapping orbits, and then we have a observation orbit, and then also a station keeping orbit. So in the survey orbits and the high and low altitude mapping orbits, that is where we are doing our science. So this is all before the mitigation mission. So we are using cameras and spectrometers to figure out what is the shape of the asteroid, what is its size, what is the mass, what is it made out of. And all of those pieces of information are very important for us to design our mitigation mission because of the wide parameters that we were given in the start. So this is a little clearer to see what the orbits look like. So on the left, we can see our survey orbit, which is the green one around the asteroid. And then we move closer in our high altitude and our low altitude mapping orbits because the specific instruments that we use, the closer you are to the surface of the asteroid, the more accurate information they give you. And then after our low altitude mapping orbit, we move to an orbit of 1,000 kilometers around the asteroid. And there we stay and we hang out until the mitigation mission comes by. And if we're there, we can observe the mitigation mission and we can send data on was it successful and what happened, and maybe take some pictures and stuff. So the instruments that we have is we have images for the surface topography and the internal structure to figure out those characteristics of the asteroid. Then we have a spectrometer that's used to figure out the mass and the mineral composition. And then a laser altimeter is used to generate a shape model and figure out what is the rotational state and the gravitational attraction. And then finally, an X-band transponder, which is used for communication as well. That is used to figure out what is the gravity field of the asteroid. Because it's important to know how much gravity there is so that we don't go too close or too far away from it. All right, so after we have completed all of our science, we will observe the mitigation mission and the detonations. We'll do this to give an extra form of redundancy of if the detonation occurred, and we'll send data to Earth on how successful it was, or how it worked, or how it didn't work. So in our loiter distance, we will need to be able to see the detonations. So we need to make sure that we're in the right point of our orbit. And So that's why we'll be in that 1,000-kilometer orbit. So this is a risk chart for the THEO mission. So it's important to look at your spacecraft and look at your mission and assess what are the risks, what are the likelihood that they happen, and what is the consequence. Because when you are assessing your risks, you can design for the worst case or the best case scenario. So for example, if we look at risk number 8, if we have a failure after the culmination of a science mission, there's a pretty high likelihood of that happening because a spacecraft that only spent 2 years in development time, but needs to have a lifetime of about 15 or 16 years, it's quite hard to design for that. So there's quite a high likelihood of that happening, but the consequence, if that happens, is pretty low, because we have built redundancy into the MUFN mission, and the main point of the THEO mission is to be a scientific mission. So if it fails after the science has been completed, thankfully, we would have gotten our data and everything is fine. So that's kind of like how we look at a risk chart and how we assess our risks. And so if we had anything kind of like in the red blocks, then we would have to redesign whatever that part is, because it's very hard to build redundancy for something that's like in the red. So kind of like yellow is where you're hoping everything is. So the next part of the mission, the more exciting part, in my opinion, even though this is not mainly what I worked on, is the MUFN spacecraft. So we're sending a nuclear device into space. So much fun. So this mission will have a longer development time, a 5-year development time. That is much more nominal for what spacecraft development times would be, even though it's still pretty short. Then the spacecraft will have a 2-year lifetime until impact, so until it reaches the asteroid and completes its mission. So the mitigation method that we have here, like I mentioned, is a nuclear standoff, and I'll explain later how that works. So the minimum change in velocity that we need to impart to the asteroid before it impacts Earth is 25 millimeters per second. And so for reference, that is approximately equivalent to sending the mass of 10 to 15 SLS rockets to the asteroid and like just hitting it with them. And so that is why we are sending a nuclear detonation method instead, because just hitting it with a bunch of mass is very ineffective. So the launch vehicle is a Falcon Heavy expendable. It's the same that we have the same launch vehicle for both MUFN and THEO. So let's talk about what is a nuclear standoff detonation. So the NED is detonated a set distance above the surface of the asteroid. And so what happens is, it's not like, if any of you have seen the Oppenheimer movie, this is a very odd time to bring that up. But it's not like in the movie where you have like that giant shockwave and like there's all this smoke and all this like lights and everything. Because you're in the vacuum of space, you have a very targeted kind of like laser focused shot of energy at the asteroid. And so what that happens is it vaporizes a thin layer of the surface of the asteroid. And so that vaporization causes a momentum transfer and then a change in velocity of the asteroid. So that's kind of like, you can kind of think of like if you're sandblasting something, but instead of like particles of sand, it's particles of nuclear energy and the thing is an asteroid. That's kind of like the picture you can think of. So how MUFN is going to work and what it's going to do. The SpaceX Falcon Heavy will launch the MUFN spacecraft bus, and it will have 4 NED-equipped Baylor sats. I'll get to those a little later as well. So once MUFN reaches the asteroid, it'll station keep a distance away from the asteroid, and then it will release a single NED-equipped balesat, so basically a single nuclear device, will be released from MUFN, and then it will detonate in front of the asteroid. In front being relative, that just means 180 degrees away from where MUFN is. And so after that detonation has been completed, MUFN will complete a revolution to take pictures of the blast site and see if it was successful and what's going on. And then we will repeat that process of sending a balesat and detonating it and doing a rotation around the asteroid until all of the balesats have been detonated. Okay, so how do we choose how big the nuclear device is supposed to be and how many we need? I mentioned we need 4 of them. So your imparted delta V per kilogram of the nuclear device mass. So this table here contains a lot of information that I'm going to try and convey. So you get more imparted delta V if you have a smaller nuclear payload. And that sounds counterintuitive, but it's because once you have kind of like detonated your device, it can only impart so much energy to the asteroid. So there's a sweet spot in between it being too small, and then it can also be too big so that you have a lot of wasted energy. So that's why you don't just go for the biggest, strongest one that you can find. So each MUFN spacecraft will have 4 340 kiloton NED balesats. So these balesats are just like small little spacecrafts that will move from the MUFN bus and then detonate at the asteroid. So each balesat detonation will impart 2.3 millimeters per second of delta V. And so that will give us a total of 27.8 if we do 3 Falcon Heavy launches of 3 MUFN spacecrafts, each with 4 NED-equipped balesats. So that's a lot larger than the 25 millimeters per second requirement. So another thing about the nuclear explosive devices that makes them very good for this type of application is depending on how far away you are from the asteroid, you get more or less energy transferred from your NED to the asteroid. So if we get there and we realize it's a lot bigger or a lot smaller than we designed, we can either move closer or further away from the asteroid with our balesats in our detonations. All right, so this is our vehicle design. So the giant tube on the outside, that represents the fairing of the Falcon Heavy. And so that little small guy down there, that is our MUFN spacecraft. And you can see the little 4 squares on the side representing the balesats. They have a cute little picture of a dog on there. So we will send up, I think I said 3 of these, each with 4 of the little balesats to complete our mitigation mission. And then the tables have like a bunch of very interesting jargon of like the mass and stuff like that of the spacecraft. So the trajectory of the MUFN spacecraft is a lot similar to that of THEO. We also found the launch periods and the kind of like trajectory design in a similar manner as we did with MUFN. Let me just let that go away. Oh no, go back. Okay. So we found it in like a similar manner with the mass delivered charts and stuff like that. So we have about 5 launch periods between 2028 and 2029 where we could launch. And so again, each launch period is like 21 consecutive days in which we can launch on any one of those days and our mission will be successful. And again, our launch vehicle is putting us into that inclined orbit so that we don't have to do that because that's a lot of delta V. And so we can see here the total delta V is about 3.5 kilometers per second. And that's higher than it was for the THEO spacecraft. And that's because obviously the spacecraft is a lot heavier than the THEO spacecraft was. So we need a little more change in velocity. So as a quick conclusion, the MUFN spacecraft will launch on 4 separate Falcon Heavies. Each one will have a MUFN mitigation spacecraft with 4 Baylor-sats on it. And so we only need 3 MUFN deliveries to have a successful deflection of the asteroid. We have designed our mission to have 4 of them for in case something goes wrong with one, or if some of the Baylor-sats, something goes wrong there, then we have an extra one as redundancy. And then after the detonation will clear, MUFN will, of course, survey and deploy the next Baylor-sat. So we have designed for a total of 27.8 millimeters per second of delta V to be imparted to the asteroid. But because we have a 4th redundant MUFN spacecraft, we can impart 37.1 millimeters per second of delta V to the asteroid. So that is, if we get there and we realize it's really, really, really big, then we can just send that extra spacecraft. So the missed distance that we will send the asteroid into, so the new orbit that the asteroid will be in, will